Today our topic is simplifying radicals. So our learning target is how can I get radical expressions into simplest form. A radical expression in simplest form is in simplest form if the following conditions are true. No perfect square factors other than 1 are in the radicand. Remember, radicand is the number underneath the radical. So here, square root 10, 10 would be the radicand. No fractions are in the radicand. So we wouldn't want to have the square root of 7 over 4. And no radicals appear in the denominator of a fraction, so we could not have 7 over the square root of 4. That would not be in the simplest form. All right. Product property of radicals. The square root of a product is equal to the product of the square roots of the factors. So what that just means is that if you were multiplying two numbers together, so like the square root of 6 times 9, that would be equal to the square root of 6 times the square root of 9. This allows us to simplify things because we know the square root of 9 is 3, and then this would be the square root of, this would be 3 times the square root of 6. All right? This also works the other way. If we have the square root of 5 times the square root of 7, we can rewrite that as the square root of 5 times 7, which is equal to the square root of 35. All right, so we want to use this product property to simplify these radicals. And every time you see that word simplify, when talking about radicals, that means we want it in the simplest form. Okay, so the square root of 32, we want to try and break that down into two square roots, so the product of two square roots, where one of those square roots is a perfect square. So we have to think factors of 32. 2 times 16 gives us 32. 16 is a perfect square. We want perfect squares, because then we can say that the square root of 32 is the square root of 16 times the square root of 2. And then we know that the square root of 16 is 4 square root 2. So the square root of 32 is actually equal to 4 square root 2. Square root of 9 times x to the third power. So let's first just break that down. Square root of 9 times the square root of x to the third. Put the variables in its own square root. Square root of 9 we know is 3, so that's good, times the square root of x to the third power. Now let's break down x to the third power. We want a perfect square, and a perfect square would be x squared, and then this would be times x. So we can actually say that this is 3 times the square root of x squared times the square root of x. Square root of x squared is just x times the square root of x. It does get more complicated when there are letters involved. All right, so then 3x times 4 times the square root of x. We want to start by getting these two radicals together. So like this example, when we had two separate radicals, we can put them underneath one radical. We can actually say that the square root of 3x times the square root of x is equal to the square root of 3x times x, which would be equal to 3 square root x, the square root of 3 times x squared. All right, so really this is 4 times the square root of 3x squared. Then we want to break apart the number and the radical and the variable, my apologies. And then 4 times the square root of 3, the square root of x squared is x. We always want to have all of our numbers outside of the radical in front of the radical. We want that radical to be last. So this would actually be 4x times the square root of 3. Next example is the quotient property of radicals. Works the same way as the multiplication one, except for now quotient we're working with division. So the square root of a fraction is equal to the square root of the numerator over the square root of the denominator. Okay, so here in this example we have the square root of 16 over 25. We can break that apart to be the square root of 16 over the square root of 25, which then allows us to simplify to 4/5. Pretty simple. If we look at example 2, we have the square root of 13 over 100, so this would be the square root of 13 over the square root of 100, which equals the square root of 13 over square root of 100 is 10. Now, the reason we need this property is because no fractions are in the radicand. We could not leave this fraction 13 over 100 and call this in simplest form, so we're simplifying. All right, next example, we have the square root of 7 over x squared, so break that apart into two radicals. Square root of 7 over the square root of x squared would be the square root of 7 over x. Last one, we have 7 over the square root of 7. Now this goes with this last rule. No radicals appear in the denominator of a fraction. We cannot leave that radical there. So how we get that out is to multiply by a fraction of the denominator over the denominator. We just take the number, the square root that's in the denominator, and multiply it by that fraction. So the top becomes 5 times the square root of 7. The bottom, the square root of 7 times the square root of 7, we can rewrite as the square root of 7 times 7. Simplify, 5 square root 7 over 7 times 7 is 49, so the square root of 49, which we know is a perfect square, so 5 square root 7 over the square root of 49, which is 7. Next, on the back of your page, adding and subtracting radicals. You can add / subtract like radicals. And that would mean they have the same number in the radicand. So if we look at example 3, 4 square root 10, square root 13, negative 9 square root 10, we have two like radicals that we can put together by doing 4 minus 9, negative 5 square root 10, and then we add the square root of 13. That is as simplified as we can go. 5 square root 3 plus the square root of 48. Now the square root of 48 is not in simplest form, so we need to factor that first. Factors of 48 would be 4 and 12. 4 is that perfect square. And factors of 12, 4 and 3. 4 is that perfect square. So we can rewrite the square root of 48 as the square root of 4 times the square root of 4 times the square root of 3 using these factors. We know the square root of 4 is 2. Square root of 4 is 2. Square root of 3 stays the square root of 3. 4 times 2 times 2 is 4. So the square root of 48 is really 4 square root 3. So we are doing 5 square root 3 plus 4 square root 3, which is equal to 9 square root 3. Last example here, 2 square root 7 minus 3 square root 63. Square root of 63 is not in simplest form. Factors of that would be 9 and 7, where 9 is that perfect square. So we can rewrite 3 square root 63 as 3 times the square root of 9 times the square root of 7. Square root of 9 is 3, so we have 3 times the square root of 7. 3 times 3 is 9. We have 9 square root 7. So we're really doing 2 square root 7 minus 9 square root 7, which is equal to negative 7 square root 7. Last example, multiplying radicals. When we multiply radicals, you can multiply numbers outside the radical and multiply numbers under the radical. So if we look at this example, first off, we are going to have to distribute. So we have the square root of 5 times 4 minus the square root of 5 times the square root of 20. So what I mean by numbers outside the radical is 4 is not underneath the radical, so that would be outside the radical. 5 is under the radical. So we can't put these two together. We just have to leave it as 4 times the square root of 5. But remember, we always want the square root last, so we put that 4 in front. Minus, we can multiply numbers underneath radicals. So 5 times 20 we can do. So we get the square root of 5 times 20, which then gives us 4 square root 5 minus the square root of 100, because 5 times 20 is 100. And then we get 4 square root 5. Square root of 100 is 10 minus 10. We can't simplify that any further. Last example, we're multiplying a lot of stuff. We've got 2 terms here and 2 terms here. So if we remember when we multiplied polynomials, we used that box method. We're going to go back to that. So we have the square root of 7 plus the square root of 2. And then we have, in our second parenthesis, square root of 7 minus 3 square root 2. Square root of 7 times the square root of 7 becomes the square root of 7 times 7. Numbers underneath the radical go together. Negative 3 square root 2 times the square root of 7. Negative 3 is by itself times the square root of 2 is under the radical times 7, which is under the radical. Next row, we have the square root of 7 times the square root of 2. So both numbers are under the radical, so they stay under the radical. And then our last pair, negative 3 square root 2 times the square root of 2, we get negative 3 times the square root of 2 times 2, because 2 and 2 were both underneath the radical. So if you notice, numbers that were under the radical stayed under the radical. Numbers that were outside the radical stayed outside the radical. Now we just need to simplify. We have the square root of 7 times 7, which is the square root of 49. Then here we have minus 3 times the square root of 2 times 7, which would be 14. Here we have the square root of 7 times 2. It's positive. And the square root of 7 times 2 would be the square root of 14. Minus 3 times the square root of 2 times 2, which should be the square root of 4. Yeah, I can keep simplifying. Square root of 49 is 7. Negative 3 square root 14 plus 1 square root 14, they have the same square root, so we can add the numbers. Negative 3 plus 1 is negative 2. Tack on that square root 14. Minus 3 times the square root of 4. Square root of 4 is 2, so this would be negative 3 times 2, which would be minus 6. Last, put those numbers together. 7 minus 6 is 1, so you have 1 minus 2 square root 14. That's all the notes I have for you today. Thank you for watching this video, and please subscribe to my YouTube channel.